Good morning. Now we've warmed up a bit here in the class before starting the recording with this task. So let's begin. And once we've done that, we'll go through the program I have written over here. We will continue to look at linear equation systems and learn a bit about them. And in that context, we will look at what the general solution strategy is for solving systems of linear equations if you are doing it by hand. You can also do it in calculation programs like Maple, for example. Then I will show you a couple of examples and give you a few exercises. And you will also learn about the concept of rank. It turns out that it makes sense to talk about rank, which is the number of leading ones you can produce if you perform Gauss-Jordan elimination on a total matrix. And finally, we'll look at something called the inverse matrix. It's a super smart way to solve linear systems. However, you can only use the inverse matrix if there are as many equations as there are unknowns. So it requires that the matrix you get when you write down the coefficient matrix is what we call square, meaning there are equal numbers of rows and columns. Then one can use the concept of an inverse matrix, and it also requires that the determinant is different from 0. But we'll get to that. So let's start with the warm-up task here. What is written here is the problem. There are two numbers you do not know, x1 and x2. And you know that if you take twice x1 and 4 times x2 and add them together, it gives the number 22. Now you also know that if you add the two unknown numbers directly, it equals 7. So you can probably quickly guess, just by looking here, that the solutions are 3 and 4, because you can see 3 plus 4.
Jesus.
And 2 times 3 is 6, plus 4 times 4 is 16, and 16 plus 6 is 22. So you can guess it. But that's only because I've made sure the numbers are so neat. It's far from always possible to guess the solutions to your equation system. And that's why we need to learn to solve them more generally. And that's why I have guided you through the solution method here. The first thing you need to do is understand what is meant by the coefficient matrix, which we usually call A, and what is meant by the total matrix. A coefficient matrix means writing a rectangular array with all the numbers on the left side of the linear system, and it shows 2, 4, 1, 1. Typically, you don't write the ones, so you need to spot them yourself. If we start from the beginning, I can write down the coefficient matrix for this linear equation system. It is 2, 4, 1, 1. And such a thing is called a matrix. It is just a rectangular table of numbers. You describe its size by indicating the number of rows and columns. Here, there are 2 rows and 2 columns. So we call it a 2 by 2 matrix.
So this is a 2 by 2 matrix.
And when you specify the size of a matrix, you must state the number of rows first, and then the number of columns. So it's the number of rows, and then the number of columns.
And it's good to be able to say that if you make it through this to the end.
You must be able to explain what a coded matrix is. If you can't, it's a sure way to fail.
And you don't know what a coefficient matrix is.
Yes, then you fail immediately. See the Elvis chord progression.
If you know that, you're well on your way to passing. Make sure you know what a qualification matrix is for the final exam.
Then one can take this coefficient matrix and merge it with the right-hand side. And the right-hand side is the two numbers, you know, that are up here on the right. So it looks like this. And again, remember to write 2 lines down for the exam.
And below to indicate that it is a man.
6. So you simply rate to
qualify
2,
a matrix
4,
on 1.
And then you can draw a dashed line and write the right side up.
And there it says then.
Then you go and write. And here is all the information needed to solve the system of equations. There is no need to carry around the x1 and x2 symbols to solve the system, because it is clear that the solution to such a linear system of equations depends solely on the numbers that are written here. So by writing down these numbers, you have everything needed to solve the system of equations. And now Gauss, along with Jordan, has invented a method, which we call Gauss-Jordan elimination, to bring this matrix to what we call row echelon form. And what was triangular form again? Well, it was when there were 1s in the diagonal and 0s outside the diagonal. If you can do that, you rearrange it so there's a 1 there, a 1 there, a 0 there, and a 0 there.
So the display is over here.
Is it easy to understand why the solution would be over here if it says 1, 1, 0, 0? Try writing it down like this. 1, 1, 0, 0, and then the right side And let's just write the numbers 3 and 4. So what exactly have I written? I've noted that 1 times x1 plus 0 times x2 should equal 3. So it simply states here that x1 is 3. The only thing stated here is that x1 is 3 because there are 0 instances of x2 here. And what does it say in the row below? It says 0x1 plus 1x2 must equal 4. So it directly states that x2 is 4. Therefore,
A bit chaotic on
if
Friday.
you can transform that into that, you've performed what is called
And then
Gauss-Jordan.
one is set free, just in a system.
So we somehow need to see if we can get from there to there. And we usually write a symbol like this here. So now I'm writing a new augmented matrix for a new system of equations with the same solution set as that one. So you must not use equal signs. You should use that symbol. The first thing I want is a 1 there. So I multiply row 1 by 1/2. And that is called a row operation. So up here, I intend to take row 1 and multiply it by 1/2. If I multiply by 1/2 there, I get 1. I multiply by 1/2 there, I get 2. I multiply by 1/2 there, I get 11.
But that was the first thing.
And in the second row, I haven't done anything. So I just copy paste it and write it down as it is, like that. Now I would like there to be a 0 there because I would like to have a 0 there. And to get a 0 there, I can just take row 2 and subtract row 1. So I write down here that I'm taking row 2 and subtracting row 1. And what I get becomes my new row 2. So what you write out here is the row operation. And then you do what it says here, and you mix a new row at the place where you write the instruction. So the instruction here is for row 2, which is why something happens in row 2. And now I write that curly symbol again, which means a new augmented matrix is coming with the solution set identical to the one it has, which is identical to the solution set the augmented matrix has.
Let's try to do it.
So I'm going to have 1 minus 1, which is 0. So now it's 0. Then there's 1 minus 2, which is minus 1. It says there 7 minus 11. That is minus 4. So I need to have negative 4. Up here, I haven't done anything. Everything happened in row 2. So here I can just copy and paste it. 1, 2, 11, 1, 2, 11. And now we see that I would like to have a 1, not a negative 1. That's what we wanted. So I multiply the entire row 2 by negative 1, and then we write it. So I multiply row 2 by negative 1, and then I get what I am now writing. 1, 2, 3,
What? Hey.
11, because I haven't done anything to the top row, so I just copy pasted it. And here I multiply by negative 1, and it still gives 0. So I multiply it by negative 1 to get 1, and multiply it by negative 1 to get 4. And now we're close to being done. You can see we have a number in the diagonal, and we have 0 below the diagonal, but we still need a 0 above the diagonal. So to get a 0 there, I take row 1 and subtract 2 times row 2.
We take our 0 nose 2 times row 2.
Because you can see that if I stand here and take the 1 minus 2 times 0, it still gives the 1, so it doesn't ruin the 1 there, because there's already a 0 here. Let's do it, Dovita.
So it will say 1 minus 2 times 0.
It is still 1. 2 minus 2 times 1, that's 2 minus 2, which is 0. Now there's a 0 there. And then I say 11 minus 2 times 4, which is 11 minus 8. That gives 3. And in that row, I didn't do anything. So just copy it here, where it said 0, 1, 4. And we can now see that we have achieved our triangular form. And we see here that there are 2 leading ones. So we have reached exactly the form we want. And we can see that the solutions are x1 equals 3 and x2 equals 4. So we write it down. x1 is equal to 3, 2 lines underneath.
And double even with 4.
And already now, I can introduce you to the concept of rank. Because this one,
Total matrix, it has a rank. And what is that?
it is the number of leading ones. And there is one that is king in this column, because there are zeros underneath. And here's a leading one in this column, because there are 0 rows. And so there are no more leading ones, so the rank is 2. And you write it like this. You can write the word rank The rank is our total.
Mads, no. That's another thing.
This means that there are two leading ones.
This is 2 leaders.
It's hell. And when we had two equations with two unknowns, we cannot have a rank greater than 2 for our coefficient matrix. The highest we can have for our coefficient matrix is 2.
Just go
So it is said to have full rank. It has therefore a high rank.
Could it possibly have had fewer than 2 kids? Could it indeed?
How would my system of equations have looked if
This
the
is
rank
a-
were less than 2, meaning 1? Yes, then it would just be that this was an equation repeated below in disguise. Imagine, for example,
So I multiply the entire line through
numbers,
the middle.
for example, the number 2, where it says 4x1 plus 8x2 equals 44. It's the same equation, written again. So if that equation is just the same, but in disguise, then it does not have full rank. So what does it mean when there's full rank? It means there is exactly one solution. There is only one intersection point. If this is a straight line, I call Lone, and the other a straight line I call Morgan's, then full rank means the two lines are not parallel to each other. Therefore, they intersect at exactly one point, and the system of equations has exactly one solution.
But what if the loan is recorded twice?
So it's the same straight line that appears in both places, disguised as each other.
So if you draw the loan and then draw the loan again, you are drawing the loan on top of the loan. How many solutions are there then? Infinitely many.
Namely, all the points that lie on the loan solve the system of equations. We call that a single infinity of solutions.
And that corresponds to what we call the determinant, which becomes 0. But we'll get back to that later. So this was the one solution. Some might wonder, why do you say there's one solution when you found two numbers? Well, the one solution represents a point in the two-dimensional number space, meaning in the plane. And we are looking for intersections when solving systems of equations. So there is only one solution. And that one solution corresponds to the single point in the plane with coordinates 3, 4. And now we will see as we move down to point 3 here, we have just done this. Now at point 3, we need to interpret the solution geometrically.
Let's try to do that on the next board.
So that was number 1. May I know the shots here? So if we look again at this equation here, and we are on point 3, it says 2 times x1 plus 4 times x2 should equal 22.
And we saw that before the fall break.
This is actually the equation for a straight line. But here the straight line is in what is called implicit form, which means you cannot easily read off the slope, and you cannot easily determine the y-axis intercept. But what you can read off is a normal vector. Do you remember that? Because the normal vector has the coordinates 2 and 4. And then you can just think about it, and you can find a point that you know this line also goes through. For example, by setting x2 to be 0.
Because if x2 is set to 0,
then it says 4 times 0 here, that is 0. Well, then it says 2 times 1, so shouldn't that be 22? So x1 must be 11. So x1 tries to be 11, and that means this point here, which has the coordinates 11, 0, where this is x1, and that is x2. Empty point. It lies on the straight line written up here. And that's why I can now draw that straight line. Let me do that right away. I'll just draw it. So here's a coordinate system. Pause. This is the x1 axis, and this is the x2 axis. And then I can start by drawing that point 11, 0. It might be here. So the distance from there to here is 11. And there are lines and windows
Good
that
Monday.
pass through that point, infinitely many.
It's all the straight lines that lie and twist around the points, of which there are countless.
But what we know
is that we are looking for a guideline, namely
in
the
this
only
straight
one.
line, which is perpendicular to the vector with coordinates 2/4. So we can write down what our normal vector is for loan. If loan is the name of the line, then the normal vector is the one with coordinates 2/4. You can draw it so that it starts at that point, because you can start a vector wherever you want, but once you've started it, there's only one place a given vector can end. So if I start the vector here, I need to go 2 units out and 4 units up, meaning my normal vector looks roughly like this. This is the normal vector for loan. And now we can see that there's one and only one straight line that passes through that point and is perpendicular to the vector. And that straight line is loan.
And who describes the loan? It is the similar.
So now I can draw loans. She looks approximately like this. I'll just see if I can draw lines a bit nicer. Here is 90 degrees and here is the line.
And the loan, of course, continues indefinitely in both directions.
So we can try to look at the next one. If we call this straight line from moons, then we can draw moons. You choose. If you set x1 to 0, then you can find x2 as 22 quarters or 11 halves. I didn't do that to avoid fractions, but you could certainly have done it correctly as well. It was just to find some point you knew the line went through. Then you could simply choose one of the two variables to be 0. It is usually the easiest. All right, let's try to draw months. Months is defined as 1 times x1 plus 1 times x2, which should equal 7. And that means if we let x2 be 0 again, then x1 will be 7. So this point here, called 7, 0, is where Mons passes through.
With certainty, he goes through there.
And that is x1 and that is x2. If you take 1 times 7 plus 1 times 0, you get 7. That's correct. And Mons also has a normal vector, which I can call nm, for the normal vector of Mons, and it has the coordinates 1/1. And now I can draw Mons. So I first position myself at the point 7, 0, and if it's 11, then 7 is maybe roughly here. So Mons has to pass through here. He must pass through that point there. But at the same time, I need to draw a scale. So one goes down and one goes up. So let's say 1 out and 1 up. It might look approximately like this. It should be a 45-degree vector because we move equally out and up. And then I need to draw the only straight line that exists, which passes through that point and is simultaneously perpendicular on the normal vector from Mogens. And it is located here. There we go. Okay, Jim, maybe it's not quite drawn well. Try it again, like that, maybe. Here's 90 degrees, and you can see the two, Lone and Monas. At the precise point 1, I'm drawing a bit nicer here. Then we move 11 up there, and 7 was here, and this is Mons's name. And what we can see geometrically is that we have found the only place where Lone and Mons have something in common, the point where they intersect. And here we have, if I had drawn it perfectly, I would have 3 here, because I found the exit to 3, and here I would have 4. So I can see geometrically, one can interpret it as the intersection between 2 straight lines. That is the meaning. But you can also interpret the geometry in another way, like this. You could do that because you know it's there. But if you need to check if the calculations are correct, it might be more strategic to go the other way and see if it fits. Not perpendicular by being switched around. I didn't understand that. I still don't understand you. I can understand the idea of starting by drawing this point and then saying, okay, I know they have to intersect here. And then draw the lines afterwards so they pass through that point. But I would rather do something else, like what I did. Because first, on with boys and for 3 and 4, then I'd like to see if it fits. So as an extra check, you could say I quickly sketch lines and see if they intersect at points 3 and 4. And they do. So it would be better not to assume you calculated correctly, but to verify it with your drawing. And that's a big part of being an engineer. It's about constantly being skeptical of yourself and your own calculations, and then finding different methods. So I end up at the same place with different methods. So this is one way to interpret it with a drawing. And when I say interpret it with a drawing, mathematicians call it geometric, but you can interpret it in a way more geometrically. And let's take a look at it once more. This must have been board 2. So it's no longer take 2, because now I will write it out. So now it becomes board wood. So let's just try to look at the other interpretation. And for that, we might just need to
Wipe it all once as it is.
What does it actually say here?
if we look at this line and that line simultaneously, you can see that x1 is multiplied by 2 and x1 is also multiplied by 1.
How could I write that down? Well, we can write it like this.
x1 has been multiplied by the vector that has the coordinates 2 above. If you look over here, what has x2 been multiplied by? It has been multiplied by 4 and 1. So I can write it like this. x2 is multiplied by the vector 4 over 1. And what should it give for a vector on the right side? Well, it should give 22 over 7.
2 and 2 is equal.
So what you can see I have done now is I have taken 2 equal signs and magically turned them into just one. Look at what it says. It says 2 times x1 plus 4 times x2 should equal the first coordinate, 22, because this is a vector. And this is a vector. If 2 vectors are to be equal to each other, they must have the same first coordinate and the same second coordinate. And what is the first coordinate over here on the left side? Well, it's 2 times x1 plus 4 times x2. Can you see that? And what is the second coordinate over on the left side here? It is 1 times x1 plus 1 times x2. And that should equal. So you can see that I have actually written 2 equations with 2 unknowns. I've written it up all at once as a vector equation with just a BAPE. And what is written here can be interpreted geometrically.
Because what is that? It's a known vector.
And that is a known vector. And that is a known vector. So what is actually written here is, dear Jim, would you please scale that vector with the scaling constant in the clip? And scale that vector with the scaling constant x2. And then when you add them together afterward, you should get that vector. You can do that. It is said that you have formed that vector by linearly combining this vector and that vector. And we call it a linear combination.
And it can be drawn. And because it can be drawn, that interpretation is geometric.
So let's draw it. So let's draw a coordinate system where we can sketch the story. And again, the coordinate system has a bit of an odd name. Now it's not called xy, it's called xc and x2. And that's typically the naming we use when there are many unknowns. x1, x2, x3, x4, up to xn.
Then you get an n-dimensional space. But right now there is only
live in the
so it's luck.
two-dimensional space in this story.
So I can draw that vector first. It goes 2 out and 1 up. So let's say this is 2 out and this is 1 up. So here's a nice little vector. That's the vector there.
And get the handle.
You can imagine that. So I can just call this vector v.
So that's what I evaluate it by. It's a little sweet balance for that.
It points directly and writes vector A.
And this weight, well, I
and
can
call
handle
it the b vector.
And this vector over here, I can call it the C vector.
What does the b vector look like when it goes 4 out and 1 up?
There were 2, so this must be about 4.
And then it goes up by 1. This is how it looks.
So this is vector B.
And now I need to draw vector c. That's a bit more
Because it goes
complicated.
22 out and 7 up, right? So if it's 4, then it's 4.
Let's change 25 to 22 around here. And then 7 up. And that's maybe about there.
You can see that I'm a bit sloppy with the drawing. It's just to give you an idea of what it's about. Here is x1, and here we assume there are 22.
And again, we have one that is sick.
So the switch starts here and ends up there.
It looks like this.
And that is vector C. That's what our task is about now. It's about saying that if you have this little cute vector, and you have that little cute vector, can you form that one?
Each combines the two equally closely.
And that means you have to multiply this vector by a number to scale it, so it becomes longer. And you have to multiply this vector by a number to scale it, so it becomes longer, or shorter, or changes direction the other way if you need to, every time with a negative number. And what you need to achieve is that if you add the scaled version of A with the scaled version of B, you should get vector C. Can you see what it says? This is a scaled version of A, and this is a scaled version of B. Together, they should equal C.
And you'll notice that if you take 3 and do it like
Every time I
this,
scale it, it becomes 3 times longer, approximately like that. If you take 4 and multiply it by B, it looks approximately like this. But this is the separated version A, and this is the separated version B. So this is 3A,
And this is class 4B.
and now I hope you can see that if you use the parallelogram rule, then that vector plus that vector will give that vector. I just need to draw a parallelogram here. And can you see that that vector lies as the diagonal in this parallelogram? But that must mean, if it does, that vector C is the sum of 3A plus 4B. And one of the oral questions for your exam is about precisely that. And interpret a line system geometrically in 2 different ways. And those are the 2 ways, either as the intersection between lines or as linear combinations of vectors. And that interpretation
Can only be drawn if you are in 2 dimensions.
that is if you are in 3 dimensions. Well, then it is the intersection between not lines, but planes instead. So if you have 3 planes, they can intersect at a single point. 1 plane here, 1 plane here, and 1 plane here, if they intersect at 1 point. That single point is the solution to a system of equations. If the rank is full, if you have full rank, there are 3 leading ones in a 3 by 3 coefficient matrix. Then there is exactly 1 solution. It corresponds to exactly 1 point in 3-dimensional space that the 3 equations share. And that is the solution. What if the rank is not full? What if the rank is not 3, but 2? Well, then it is the intersection between 3 planes, where 2 of the planes are parallel. Or if 2 of the planes coincide, then the solution becomes a straight line in space. And now you get a single infinity of solutions. So if the rank is 1, then there is only 1 leading one, resulting in a double infinity of solutions, as we discussed during a fall break. But more on that later. So this was the warm-up exercise. Does anyone have questions about it? One cannot say which is best because both things are the same. What you are supposed to discover is that it is actually a vector equation, and it is also a matrix equation, which I will get to in a moment, once we have introduced something called matrix vector multiplication.
So you suddenly start to understand a department from all sorts of different perspectives.
And can see it geometrically in several ways. And that's what's so cool about mathematics, that there are so many ways to understand it. And there was a famous physicist named Richard Feynman who received the Nobel Prize, I believe it was in 1968 in the United States. He said that to truly understand something, you need to understand it in at least 3 different ways.
We're about to get the whistle cards ready.
And that's what we can do with mathematics. There we can visualize it in all sorts of fascinating ways. But should we start with a 10-minute break? Then we'll say we meet again at 1:45. If you want to pause the recording, you can.
I hope you had a nice break. Let's continue.
And let's just revisit.
An example I've calculated for you before. Then I can tell you a bit about the new theory around that example. of course, it's not so bad to get something new. And it's an example with this bottle and cork, if you can remember it.
So it was something about having a bottle.
I call that F, the price of it, and a cork, I call that P, on the bottle, on the cork. Then we were told that altogether it cost 5 kroner, and then we would write it like this: the bottle's price plus the stopper's price equals 5. It was an equation with two unknowns because I don't know either the price of the bottle or the price of the cap. I just know that together they cost 5 kroner.
And then we were also informed that
The bottle costs 4.5 kroner more than the cork, meaning if you take the price of the cork and add 4.5 kroner, then you get the bottle's price. Notice that neither the price of the bottle nor the stopper is known. So there are two unknowns, F and P, and two equations. So this is an example of a linear system of equations with two equations and two unknowns. And you should be careful about looking too much at the board where they are written and check it through for myself over here, because I end up swapping the bottle and the cap in equation 2, which I find puzzling. But the bottle is more expensive than the cork. So it is because the bottle costs more than the cork. How much more? 4.5 more than the cork. If we write the two equations in standard form, it will look like this. So we need to align the unknowns. Here we have 1F,
Husk 1P.
should I proceed? So that was aligning 1 written again, and aligning 2 written in a similar way. Then I need to have F stand here under F. That means if I move F to the other side, it will become minus F. And plus M up here. And then the 4.5 moves over here as minus 4.5. So now I've written the same two equations again, but now I've written them in standard form. So we can directly read off the coefficients 1, 1, minus 1, 1. And the right side becomes 5 and minus 4.5.
All clear.
Let's try to solve this system of equations using Gauss-Jordan elimination. We begin by writing down our augmented matrix for the system of equations. And it will be like this.
1, 1, minus 1, 1.
And then the right side, 5 and negative 4.5. And I am sticking to physicist notation for this task instead of mathematicians. They would call this minus 9.5.
But I call it the minus 4.5.
I ended up rating it like a physicist. And now we're going to perform Gauss-Jordan elimination and bring this total matrix to reduced row echelon form. And the first thing we see is that there is already a 1 here. We like that because we have a leading 1 there. Soon when there is a 0 here and a 0 there. So we don't need to do anything here. But down here we want a 0. And we get that by adding row 2 and row 1 together. I take row 2 and add row 1. And what I get from that is the following. 1, 1, 5 still remains. And I haven't done anything there. And down here, I get minus 1 plus 1, which is 0. 1 plus 1, which is 2. And minus 4.5 plus 5, which is plus 1/2. So I get this. And now we want this number here. So multiply row 2 by 1/2. (1.1.5), we can copy and paste that. When I take half of 0, I still get 0, and half of 2 is 1. And half of 0.5 is 0.24. So I need to have 0.24. So now I have a leading 1 there. I just need to get a 0 there to be finished. So now I can take row 1 minus row 2. And then I end up with 1 minus 0 is still 1. 1 minus 1 is 0. And 5 minus 0.25 is 4.75. And down here it says 0.1 and a 0.25. And then we solved it for her. So we can see here that 1 times the price of the bottle plus 0 times the price of the cap gives 4.75. So the bottle must cost 4.75. And 0 times the bottle's price plus 1 times the cap's price gives 0.25. So the cap must cost 25. And that is the solution system. And now we will write that this system of equations if we look at our total matrix and want to indicate the rank, we write it like this. The rankskeg
Of our total matrix.
Someone came up with the idea that you can write it this way with a row, and then you don't have to write the word rank. So the rank is our total matrix. What is that? Well, it is the number of leading ones, and there were 2 leading ones, so the rank is 2. And we can also see that if we ask what is the rank of our qualification
Ended
number,
with a thud.
it is actually also 2, because you only need to look at what is over here. You might also encounter a 1 here that was a leading one, but we don't have that. So we have the same rank for our qualification matrix. It is also 2. And since our qualification matrix was a 2 by 2, we can just write it up here. Here we can read off what our qualification matrix is. The one called 1, 1, minus 1, 1, 1, 1, minus 1, and 1. This 2 by 2 matrix has a rank of 2, and it cannot have a rank higher than 2 because there is not room for more than 2 leading ones in it. And therefore we say that it has full rank. So when a matrix has the largest possible rank it can have, we say it has full rank. And it's connected to the concept called determinant. And maybe you remember it, maybe you don't. It's something called a determinant that has been introduced. And the determinant for this matrix, I can show you how to calculate it.
That is the determinant of our coefficient matrix A.
You calculate it like this times this. So you multiply along the diagonal, this times this. And then you say minus, and then you say this times this. So it gives 1 times 1. And then it gives minus 1 times 1.
See you around.
If we calculate it, we see here 1. And since minus times minus is plus, it becomes 1 plus 1, which is 2. And then your brain demands to know, what does it mean that the determinant is 2? If A is a matrix with an equal number of rows and columns, we call A square matrix. In this case, A is square, so they write it down. A is square in this case. And if you have a square matrix with a determinant that is not 0, because it was 2, not 0, then it is full rank. So a square matrix with a determinant different from 0 always has full rank. I'll write that down, it's important. In January. Square matrix, and it applies no matter how many dimensions there are, as long as it is square, and what I'm writing down now.
A square matrix with before it powers down.
That are not 0. What is going on? We write it like that, right? Always full rank. And furthermore, we can say something else, which I will elaborate on later, but a square matrix with a determinant that is not 0 always has an inverse matrix. So we can write that as well. In this case, there is always an inverse matrix for A. And now I will explain what that means.
It's an introvert.
Matrix. And you rate it like this. So what I've noted here is that if you have a square matrix, and what is that again? It's a matrix with an equal number of rows and columns. And if its determinant is not 0, what does it give? 7, for example, or 2, like it does here, or -8, as long as it is not 0. Then it always has full rank, and such a matrix, if it is square and has full rank, always has an inverse, whatever that means.
And that's what we're going to look at now. What does the term inverse matrix mean?
Good evening.
And that means the example I have
The
calculated
bottle
here.
and the cork. That's an example that fits this theory precisely because I have a square coefficient matrix. It is a square coefficient matrix. Yes, I have, because there are 2 rows and 2 columns. It is square. There are the same number of rows and columns. Does its determinant give something different from 0? Yes, it does, because this times that minus that times that gave 2. And 2 is not 0. Therefore, there exists a matrix for this one. And what can you use it for? You can use it to solve the system of equations.
Instead of doing the Gauss-Jordan elimination,
Then you can use the inverse matrix to solve the system of equations. So I will briefly explain what an inverse matrix actually means here with a very simple example, so you can understand what it's about. Here's an example within another example, so you can grasp it.
And what should I call that example? 1.
If you have one that looks like this, 2x equal to 8, it can't really get simpler, right? Find me a number that multiplied by 2 gives 8. The answer is 4. So what can I do to magically change a 2 into a 1 so that there's just an x with something? Because then I have the solution. What you can do is multiply by the inverse of 2 on both sides of the equation. What is the inverse of 2? It is 1/2. Because 1/2 times 2 equals 1. Do you remember with complex numbers, there was something called the reciprocal complex number. It means the same as inverse here. So you could also call it the reciprocal matrix, but it has been decided that it should be called the inverse matrix. So what is the inverse of 2? The answer is 1/2. And you rate it like this. Isn't it correct that it says 1/2 there? Because let's just review our exponent rules. We have a power rule that says this can be rewritten as this. When the number moves underneath here, the sign of the exponent changes. Do you remember that? And this is just a cap. So a fancy way to write 1/2 is 2 to the power of -1. So if I multiply this equation through with 2 to the power of -1, it's equivalent to multiplying by the inverse matrix shortly, when we move on to solving more equations with more unknowns. So I multiply the whole equation by 2 to the power of -1. 2 to the power of -1 times 2 times x, you see? Now I've multiplied by 2 to the power of -1 on the left side, so I must also multiply by 2 to the power of -1 on the right side. And we have learned that when two powers with the same base are multiplied, you must add the exponents, and there is a hidden one there. So what does 2 to the power of -1 multiplied by 2 to the power of 1 give? It gives 2 to the power of 0, but 2 to the power of 0 is 1. So this is a tricky way to write the number 1. That's how it was before. And over here it says 2 to the power of -1, which is another way to write 1/2. And 1/2 times 8, well, that is 4, so I've solved it.
imagine if you could do the same with 10 equations and 10 unknowns.
Just need to find the inverse matrix of the quotient matrix, and then it is solved. You can do that, but it requires that the quotient matrix is square and that its determinant is not 0. For there must be as many leading ones as there are unknowns to get exactly one solution. And this trick can only be used if there is exactly one solution. And for there to be exactly one solution, the equations must be linearly independent of each other. This means they must not be redundantly duplicated. In disguise, there should be 2 distinct straight lines that, for example, intersect at precisely 1 point. So now let me show you how to find the inverse matrix for that one. And then I will explain what it means. So that will be on the next board. And I think for once, I'll write on the board
I
daily.
know I'll need the story to continue over here.
So here comes board 5.
So we have a coefficient matrix called A.
Matrix equals, and now I'm back to the story of the bottle and the cork. It's called 1, 1, 1, 1.
1, 1, minus 1, 1.
And I'm interested in whether I can find the inverse matrix for it, or what does that mean? Well, back to this story here. What did it mean to find the inverse number of 2? It meant that if I could find the inverse number for 2, then when I multiply it by 2, I end up with the number 1. So the inverse of 2 times 2 gives 1. The inverse of 10 times 10 also gives 1. The inverse of any number, which is not 0, multiplied by the number itself, gives 1. Are you with me on that? So how do I now define it for matrices? And I have to come up with something I call an identity element in matrix arithmetic. And a 1 in matrix algebra looks like this. This is an advanced determinant. This is an advanced 2 by 2 iptal. Why? Because it's an iptal written as a 2 by 2 matrix. And this is called the unit matrix. Some call it the identity matrix. I refer to it as a bit of both, depending on my mood. But you should think of it as the unit matrix. Matrices of order 2. The reason I say I'm of order 2 is because it's a 2 by 2.
So this is a 2 by 2 identity matrix.
You can almost figure out how a 3 by 3 identity matrix looks. 1, 1, 1, and zeros elsewhere. 3 rows, 3 columns with 1s on the diagonal and zeros outside the diagonal. That is a 1 in the matrix world. So what I'm looking for is, I'm looking for a thing like this. We call that the inverse matrix to A. Inverse
Fine,
matrix.
thanks.
And we are looking for it, understood, in the way that if you take it, once you have found it,
And then multiply it by A itself.
what should then give a 1, but it should not give a regular old-fashioned 1. It should produce a matrix 1. So it should result in the identity matrix. So if this is a 3 by 3 matrix, then that is also a 3 by 3 matrix, which will also be a 3 by 3 matrix, but it will be a very special 3 by 3, namely the identity 3 by 3 matrix. So it should become E. Here is the definition of what I mean when I say a prime. I mean that the matrix multiplied by A gives an advanced 1.
And there are many aspects in a speech added. We call it the identity matrix.
So let me write down the formula for how to find that A first. I haven't proven it yet. I'm just writing it down, and then I'll show that it works first, so you can see what it's about. So how would I find the inverse matrix? For the one that is there, all right, what you do is take the reciprocal of the determinant of the matrix. And when you have done that, you multiply that number. This here is a number that is here. Why is it so? Oh yes, because the determinant gave 2, and 1 divided by 2. Then I guess I'll take it. Can you see? The determinant gave, where should I continue here? It gave 2. And then you swap the diagonal elements. These two numbers here need to be swapped. It's quite easy because there's a number here in this exercise.
So I'll just do that. Then I'll write 1, 1.
And then outside the diagonal, there and there, you change the sign. So I write -1 there and +1 there. You might be thinking, why do it this way? But that will be proven later. For now, I'm just showing you how it's done. And what was it that the determinant yielded? 2. So this is the same as writing 1/2
Times 1 minus 1.
And 1 and 1.
And it turns out that when you need to multiply a number with a matrix, The simplest way you can imagine is the correct one. You just multiply that constant by every element in the matrix. So that means I get a 2 by 2 matrix called,
1 times a half, that's a half. So I need to stand for a half.
1/2 times negative. 1 is negative 1/2. So I need to set negative 1/2 and 1/2 and 1/2.
Of course, I've calculated correctly.
So this just should be a very special matrix. What kind of special matrix is that? It should ideally be the inverse of A. What does that mean? Well, if I multiply it by A, it should result in A. The identity matrix, also known as the unit matrix, which consists of all ones on the diagonal and zeros elsewhere.
And I'll just show you that it's correct if I've calculated correctly.
So let's try taking this one and multiplying it by that one there to see if it gives that result. That means I need to come up with a way to multiply us, and that's coming now.
So let's try to do it. Let's try calculating the A matrix.
The inverse multiplied by A.
So what do I get? It was called, maybe you can look here.
A
That's
half.
minus 1/2.
Spirit hate.
And I would like to try to multiply it by this matrix. So this is A prime.
And the other one I'm writing here is matrix A.
And it was called 1, 1, minus 1, 1. So I need to write that here. 1, 1, minus 1, 1. So how do you multiply two matrices like that? Well, to do that, you need to know what a dot product is. And I reviewed that for you before the fall break, and perhaps you've forgotten. But when you multiply two vectors, it's called a dot product. And maybe you remember that it's first coordinate times first coordinate plus second coordinate times second coordinate plus third coordinate times, and so on. That's exactly what you need to use here while doing this with your hands. So the left hand should do like this, the right hand should do like this, and then it becomes difficult when you have to do both things simultaneously. And you might feel a bit awkward doing this, but you just need to practice, right? Then you take the top row and the first column and multiply them. So you say this times this plus that times that. So the left hand does this and the right hand does that.
First row, first column.
Okay then.
It's 1/2. That times that. It also gives 1/2 because minus times minus is plus 1/2. 1,500. That is a whole. So what comes out now? What is it? It's the first number I need to write. And where should it go? In the first row, first column. There it is. Let's do it again. So this times that plus this times that. That's 1/2 plus 1/2. That's 1 whole. Then I take the first row, second column, times that one, plus times that one. So the left hand does it like this, the right hand does it like this. So times that one, plus times that one. So that's 1/2 minus 1/2, which equals 0.
All right, I will take the second row. Fixed page.
So the left hand moves like this, the right hand moves like that. So I get 1/2 minus 1/2, that is 0. Then I take the second row, second column, second row, second column. This times that plus this times that. That gives 1/2 plus 1/2. That's a whole. And look at what came out of it. A very special matrix emerged, namely the matrix that corresponds to the number one back when we only learned about numbers. This is an advanced one. It's a matrix one. And that's what we call the identity matrix, a 2 by 2 identity matrix.
So what have I found? I have
I have
found
a matrix that if I multiply it by A, gives the identity matrix. What does that make it? The inverse of that one. Are you still with me? As I can prove it, you can surely see that it provides the result it was alleged to give so far. You're welcome.
what can we use this for? Well, this equation I wrote before, which was 2 times x should equal 8. How did I solve it? I multiplied through by the inverse of 2. And if I multiplied through by the inverse of 2, then I said 2 to the power of minus 1 times 2 times x. I have equals 2 to the power of minus 1 times 8. And then I got x equals 4. And then we are done. Imagine if I could do exactly the same thing now with an entire system of equations. You can do that. I can write my entire system of equations like this. And now I better write up here because it is 2 times 2. I'm working on it. This is the system of equations here. The bottle and the cap together cost 50 kroner. The cork plus 4.5 kroner extra gives the bottle's price. We could rewrite it down here. It can be written like this. Imagine that the vector called x contains 2 unknowns, namely the bottle and the cork. Here, f represents one unknown and p represents the other unknown. So x is a vector that contains the 2 unknowns. So this is it. Yes, you can see it now. These are the 2 unknowns here, right? The 2 unknowns. And b is a vector that contains the right side. So in our bottle and cap example, the b vector is positioned such that it is called 5 and minus 4.5. Over our coefficient matrix, we already know it. We had written it down. That's called 11 minus 11. And if one invents a way to multiply a matrix by a vector, then it can still be shown that this is the way to write the system of equations presented here. And I'll just show you that. And afterwards, I will show you that this inverse operation with matrices can be used to solve systems of equations like this. Then you have the solution. You just need to multiply once with A inverse. Then you avoid Gaussian elimination. And it's clever to avoid that, but it requires that A is square and that A has a determinant that is not 0. So it has an inverse. And you will hear me say this many times because it's such a deep concept in the theory of linear algebra. So let's now define how to multiply a matrix by a vector. So what does this look like? Matrix vector multiplication.
If I take matrix A and multiply it by the vector x,
What does it give? Well, it does give, hey, with a push,
Unity 1.1, 1, 1 minus 1, 1. So I'll write that here. 1, 1 minus 1, 1.
and I will multiply that by the vector called x, which contains the 2 unknowns, the bottle's price and the cap's price.
So F and P.
And here it comes, where the decision was made to do it. And you can almost see that there was no choice if this was going to work. You should again be able to do this with the left hand and this with the right hand. Then you say this times this plus this times this.
Then we write up 1F plus 1P.
And you don't scrape that off. First row and first column, the result must be in the first row and first column. Then you take that times that plus that times that. It is minus F plus P.
Minus 1 degree Fahrenheit plus 1 degree Celsius.
And that is the result. And what you can see written here, what is it? It was exactly what was written here. 1F plus 1P and minus 1F plus 1P. And that should give the right side 5 and minus 4.5. So you can see that this was supposed to exactly match the right side, which was my B vector. Harmony. what did I say? 5 and minus 4.5. 5 and minus 4.5.
You can continue watching it here.
That's vector B. So now it's vector A times vector X.
Element B. So I have written my entire system of linear equations like this all at once. Now I like to solve it. And how do I solve this system of equations? Well, I transform it into a 1. And how do I do that? I multiply by a to the power of negative 1. So I multiply from the left side by a inverse to get a inverse times a gang x vector. Must give a to the power of minus 1 times the b vector. And what is really clever is that we already know what this will deliver.
That gives us the identity matrix.
So this can be written as the identity matrix
Gang X.
And that's the
to
answer.
say F first, the input tag times B.
And now you'll see something cool. What do you get if you take the identity matrix of the images?
Times X. Does anyone have a guess? X, because this one should behave like a 1.
And this is exactly what will happen. You'll say, this won't work.
Because what was the identity matrix? It was this one. 1, 1, 0, 0. And what was it that X was called again? Yes, it's called F and P. It includes the two prices, right? The price of the sink and the price of the plug. And what do I get if I say this times that plus this times that? Yes, when it gives F and when it gives 0.
I just like it.
That time, remember that we do like this with the left hand and like this with the right hand. That time it's 0 and that time it's P. But this was the X vector. And this becomes the X vector again. So you can see the clever thing is that when you multiply this matrix, called the identity matrix, with a vector, it gives you the vector itself.
So therefore X, it is X itself, and I have isolated X.
Extra nerdy.
So now I just need to figure this out, and then I have the answer.
Let's try to work out this math problem. Now we have to get that conversion. It's called 1/2. It's called 1/2 and minus 1/2. And a half and a half. And if I just multiply this on the right side, then I have the answer. And the right side was called 5 and negative 4.5. So here, it should say 5 and minus 4.5.
I hope that if I figure this out, I'll get the two correct.
If you have written notes on it, then you'll probably need to delete the last line below. It was just to show you that E times X equals X itself. So you'll have some space to finish the calculation. So what do we get? We get that row, that column, that times that, plus that times that. What does that give? It gives 5/2 plus half of 4.5. So they write down 5/2. 5/2 and minus times minus is plus. So that times that gave 5/2 and that gives plus. And this is actually another way to write 9/2 if I ignore the sign. So it says 1/2 times 9/2. That must be 9/4. Hey, can I put it? Why is there a plus? It's because minus times minus equals plus. And then it says 1/2 times 9/2, but 1/2 times 9/2 is 9/4. And then I have to say back then, it is again 5/2. And then I should say plus that time, which means minus
9/4.
and it can be calculated.
Because here there is.
If I extend it by 2, then there are 10/4 plus 9/4. That is 19/4. And down here it says 10/4 minus 9/4. That must be 1/4. And there the two solutions are written like mathematicians. And I make sense of this. The price and that price together, what does that make? 19/4 plus 1/4? That's 20/4. That's 5. So together, it cost you 5 krona. And does it make sense that this number is 4.5, greater than this one? That's also good if you just take a moment to think about it. So that, when calculated as a comment, gives 4.75. And here it says 0.25, and together it makes 5, so it matches. And why was it smart? It's because you can have Mabel find the inverse. And once you've got Mabel to find the inverse, if you don't feel like calculating it yourself, then it's a piece of cake to solve the linear system if someone comes up with a new one. A new mystery where he just changes the right side, but the only thing is that it changes the right side, because then you can use the same inverse matrix again and again and again and again. It's about time to take a quick break, and then after the break, I'll run through it all together again so you can see the whole story. Let's take 10 minutes. So when should we meet? 3 minutes past. If Sophie wants to take a break. So we're back in action. I hope you had a good break. Now we'll practice a bit on the craft of finding the inverse matrix. I'll show you one more example, then I'll write out a strip 2 by 2 by 3, and you'll try to find the inverse of them. It's a skill you need to practice a few times.
So the headline is
Inverse matrix.
inverse.
2 by 2 matrix. The method I'm showing here, it can only be used for a 2 by 2. There are methods for 3 by 3 and 4 by 4, etc. Now let's start with a simple one. Is it 36? Okay, well it is, isn't it? Thank you for that. So here's a quick example first, so you can see how I did it. I'm just creating a matrix on my own that could belong to a system of equations. So this is just something where I'm making up a matrix, and it might be called 1, 2, 3, 1. And the first thing you can notice when you are presented with such a matrix, and you're given a few of these to work with, is that the determinant is certainly not 0. And how can I see that quickly? But I can see that you cannot transform this row into that row just by multiplying by a constant. Because what do you need to multiply 1 by to get 1? 1. But if you multiply 1 by 2, you don't get 3.
This row and that row.
Row is not the same row repeated twice disguised by 1 being multiplied by a constant. Can you see it? Another way to see it is if you say that times that minus that times that, you don't get 0. Try it yourself. That times that is 3. That times that is 2. 3 minus 2 is 1. It's not 0. So here we have a 2 by 2 matrix that is full rank. If you perform the Gauss-Jordan elimination on this, you would end up with 2 leading ones. So the first thing you can do is check if an inverse exists. If you ask yourself whether an inverse exists, the answer is yes if the determinant is different from 0. And the answer is no if the determinant is 0. So you can just calculate the determinant as a check first. So what will the determinant of A be? You need to multiply the diagonal elements and subtract the product of the elements outside the diagonal. So that gives 1 times 3. That was the product of the diagonal elements, from which you subtract the product of the elements outside the diagonal. 1 times 2. So that gives 3 minus 2. Compare. And 1 is not 0. And that's always important to ask yourself, did it give 0 or not? It didn't. And since it did not give 0, the inverse exists. It can be found.
To the negative first power, that exists.
It exists. So now I just need to see if I can determine it. how was it that you did it? The inverse is found by taking the reciprocal of the determinant. Already you can see that this is where it goes wrong. If the determinant was 0, what would you divide by? 0, and then the universe explodes, and everything stops from there, right? So you cannot do this at all if the determinant is 0. But it wasn't 0, so we can do it. The determinant, thankfully, was 1. So that was the nicest determinant I could possibly think of. And then I will multiply by that with what is called the adjoint version of matrix A. And it sounds super difficult without actually being so. Let me just explain what that means. This means swap the diagonal elements and change the signs outside the diagonal. Okay. So what is the adjugate version of it? Well, this is it. So the adjugate version does just like this. Then 3 is there and 1 is there. And then you switch the signs outside of the diagonal. So -2 and -1. There you have it. Let's do that. Yes. So I need to say that it is the reciprocal of the determinant, but the determinant is found to be 1. So that gives 1 divided by 1.
Times, and then that bandit there.
And as mentioned, you find it by swapping the diagonal elements. And here it's important that you practice the language, because if you can say it, then you can also explain it until the oral exam.
So in a moment, we'll go out and practice it and say it.
And then we change the signs of the elements outside the diagonal.
-2, -1.
This gives 1, and it should be multiplied across all elements in our matrix. It doesn't change them, because multiplying by 1 is neutral.
That's why we have the answer 3, -2, -1, and 1.
And I claimed that if I have calculated correctly, then this matrix should be the inverse of that one. What does that mean? It means that if you take that one and multiply it with that one, you should get the identity matrix, also called the unit matrix.
Then we can test.
Let's just test if we calculate it correctly. So I'll just calculate what a to the power of -1 gives. Well, a first is 3 and -2 is 2.
And -1 and 1.
And I will just see what happens if I multiply it by a.
And my A matrix is called 1, 2, 1, 3.
And then we get the opportunity to practice making those gestures with our hands like that. And then first row, first column. And then you dot them as a dot product. So that times that, plus that times that. Do you check that? That times that is 3. That times that is -2. 3 minus 2, 1. Then I take this row, this column, multiply by that, it is 6. Multiply by that, it is -6. So it must give 0. Then we take that row, that column, second row, first column. Where should I write the result? I should write it in the second row, first column, so the result should be there. So that row, that column, times that, -1, times that, +1, -1, +1, that is 0. So it should be 0. And finally, this times this, plus this times this, is -2 plus 3. Then the brain thinks, sweet, because here is the identity matrix. That's good enough. I have found something that if I multiply it by matrix A in the identity matrix, then what is it that I have found? The inverse.
So here stands the entry.
Hey, and here stood A. Any questions? So you might ask, how do you know that's the way to do it? Well, it's because it can be proven, and we'll do that in a moment. And that's what you will go out and practice. But first, you should just try to learn the craft. So I'll come up with 3. With matrices, and you need to find the rank for them. And you should also double check with a test if you found the correct rank. So you need to do what I've done here 3 times just to try it out. Here come a few exercises. In all tasks, you must determine the penetration, if it exists. Okay, so it might also be that I'm sneaky and find one where there's no objection, right? But if there is one, then you have to decide on it. So here are three matrices.
I apologize for
It's
the
a bit
last
squeezed
one.
in. There wasn't quite space for it, but I hope you can read it. So try to find the inverse matrix of matrix A in all three cases.
It exists. See ya. Sophie is lying down and pausing the recording while it rains.
Did I write something wrong, Christian? Then we'll cover them at the start.
Cheers.
So thus were the tasks we could solve.
We probably got that sorted out quickly. I'm cold.
Right.
Now I can start by finding the determinant for my matrix, and I need that. And you find it by saying 2 times.
5 minus 2 times 4.
Multiply the diagonal elements first, and then subtract the product of the anti-diagonal elements, as you would say it fancy. So this times that minus this times that. So 2 times 5 minus 2 times 4, which gives 10 minus 8. That is 2, which is not 0. And since it is not 0, it means that the inverse of matrix A exists.
That means it exists.
And you can also just write it in words if you want. And how do I find that one? Well, I take the reciprocal. We don't know it yet because we haven't proven it yet. We'll do that in a moment. Then you need to take the reciprocal of the determinant. And the number you get from that, you multiply with all the elements in what we call the adjugate of matrix A. And you find it by swapping the diagonal elements. So here I should write 5, and here I should write 2. And then you write the 2 elements again, but with opposite signs. So it is minus 4 and minus 2. And this gave 2. So here it actually says 1/2. So I have to multiply by 1/2, and therefore I get 5/2 here.
Minus 4/2, also known as minus 2.
And here I divide by 2. So that gives negative 1 and 1. So that should be the inverse. Do you agree?
So that was the first task.
Exercise 2. Again, I start by finding the determinant. And that gives 1 times minus 2.
Multiply negative 2. Negative 5, multiply 3.
So that gives minus 2, minus 15, which is minus 17. So now I can find the inverse. I know it exists. Now I can find it. The inverse becomes the reciprocal of negative 17, which is negative 1/17. And you can put the negative here at the top if you want. I think it looks a bit odd when I write it down there, but that's how it is. Then we multiply it by the adjugate version of this, which will contain negative 2, 1, negative 3, and negative 5. Again, I have swapped the diagonal elements and changed the signs outside the diagonal. So I get minus times minus, which is plus 2/17. So here it should say 2/17. It should say 3/17. Here should be 5/17. And here it should say negative 1/17.
And then we are done. That could be the introduction.
Hello again, Jürgen, as well. And in problem 3, I calculate the determinant first and discover that it equals 0 because it is 1 times negative 6, which is negative 6, minus negative 2 times 3, which means negative 6 plus 6.
Minus 6 plus 6, that is 0.
And that means A to the negative first does not exist.
That's it.
And if you then want, you could just check that it really is the inverse by multiplying it with A and see that it gives the identity matrix. Let's wrap up today by proving how to find the inverse, and then we'll go practice it, as it's one of your oral questions. Now we would like to prove it.
And can I erase the case? I can, right?
And the proof is a bit of hocus pocus, because you can see that most proofs in mathematics are based on a good idea. And this proof is too. So you never really get a complete explanation when you think about the person who came up with it. In reality, he probably just stumbled upon it. Because he had stumbled upon it, he could then say it was true, right? And that's how proofs work.
So here comes a claim and then a proof.
Here is the theorem. Mathematicians call theorems propositions. So now I'll write down a statement. And sentences are typically formulated in such a way that no one understands them, except the person who wrote them, right? But I hope I can translate them into Danish.
One letter. A matrix each one.
How dramatic. Regulars.
2 by 2 matrix.
What have I written here in Danish? It says matrix A. It has an equal number of rows and columns, so it's called square. Its determinant is not 0, so it's called regular. If its determinant is 0, then it's called singular. And it's a 2 by 2. So there are 2 rows and 2 columns. What's written here is to imagine that you have such a matrix, which is square, 2 by 2, with a determinant different from 0. That's actually what it says, because that's what regular means.
Enjoy.
It's tough. Example.
Matrix inverse.
At least in the first place.
It is indeed.
And then we turn it up. Here comes the statement. You find the inverse by taking the reciprocal of the determinant of this matrix and multiply that number. On the adjugate version of matrix A, and here it follows that the A matrix looks like this.
A, B, C, D.
Oh, the adjugate of matrix A. It looks like this. It's called a B in the proof because it's a bit easier to write. It looks like this. You just switch those two around. And I write DNA there. Then you change the sign on them. And that's when a good idea comes.
Someone discovered that it was a good idea to look at that matrix to find the inverse.
So the proof doesn't go deeper than just noticing that it matches with symbols. It's the same great idea. That it is true. That this is how you do it, as stated here. So let's try to prove it. And to prove it, you get a good idea. You start by taking matrix A and B and multiply them to see the results.
So the proof involves us discovering the following.
Detected. A matrix multiplied by B matrix results. So let's try that. What does A times B equal?
Well, the A matrix, it's simply called A, B, C, D.
And on P.
Which is also known as juggle performance.
The addition is off. Apparently, someone came across one where he rearranged the diagonal elements and changed the signs outside. So I'll write that down.
So it will say D minus B minus C and A.
Like that. And now we'll try to perform this matrix product. And then we have to get our hands on it and do like this with one hand and like that with the other, right? So it becomes AD minus BC.
because there's a minus there. You have to say this times that plus this times that. So AD minus BC.
Oh, it's you. Minus B.
That's what I get when I use the first row and the
These
first
numbers
column.
are in the first row, first column. So I can take the first row of the second column. That gives minus AB plus AB. Can you see that? That times that gives minus AB. That times that gives plus AB. And minus AB plus AB equals 0. So here I need to put 0 in the first row, second column, because it was the first row, and second column I dotted together using the dot product method. Then we take the second row, first column, so we get this times that, which is CD, and this times that, which is minus CD. So it cancels out and gives 0. And finally, I need to take the second row, second column. So what does that give? It gives minus BC plus AD. I'll just rearrange it as AD minus BC, so it completely resembles that there, AD minus BC.
So the brain thinks, what then?
Okay, that's a very nice matrix here, because the number here is also the one there. So I can just put this number in front. It does not hurt to put it in front like this as AD minus BC. Multiply this simpler matrix where it just shows 1, 0, 0, 1. And then I better put parentheses around here because it's this entire number that should be multiplied by the matrix. Because we have learned that you
a number
multiply
on a matrix each time all elements are combined.
Next then,
In the matrix, all elements
with
are
that
connected.
number. So repeat that
one
number.
detail at a
That's
time.
number 0. That's number 1. And then I get what's written there.
But then I realized that I already know this. ABC. Look. But matrix A is called ABCD. So AD minus BC is exactly the determinant that appears there. Then I recognize it while I'm working on the proof. Then I say, hey, there's actually the determinant of matrix A right there. Yeah, my dear.
I recognize that as well.
I've been in that situation in a previous session where it
The
wasn't called that.
identity matrix.
A 2x2 scoring matrix.
It is just like E. Are you following that? So what exactly have I discovered?
I have discovered the A matrix.
A multiplied matrix. This gives the case of the determinant in the identity matrix.
Then I get a bit annoyed that this is there, because I would rather have it just say the identity matrix. So I just divide this number on both sides. Am I allowed to do that? Yes, if it's not 0, then I can. But it's not 0 because it's the determinant, and it's not 0. Why not? Well, because it says in the sentence that it is regular, and regular means that its determinant is not 0. Since the word regular means is of full rank, so there are
Sure,
no
divide by
problems
that
on
number,
either
hey.
side.
It will say matrix A.
Multiply by 1 over the determinant. Matrix A, that is, I divide by this number, but it corresponds to multiplying by the reciprocal. Like this. And now I know that it gives E. Wait, so what does it say here? It says that here you have matrix A, and here you have a matrix that, if you multiply A with it, you get the identity matrix. So what does that make this? That makes it the inverse matrix. So this must be equal to A inverse. I have now proven what I wanted. I have just proven that the inverse matrix A is exactly 1 over the determinant of matrix A.
Multiply that special invented B max.
Said here, and indeed, that's what you call the aggregate version of whatever it gets called. So that's what it ended up being called. And it's just a small, somewhat innocent piece of evidence, but it's nice to perhaps have seen it with symbols.
Yes, that's how it's done.
So I'll run through it again.
and I'll just talk while you're finishing up your notes. Then we'll go out and practice it. 2 out of 2 boards we can find around here. So you'll get to practice it. So here comes the story again, but at a slightly faster pace. Let A be a regular square 2 by 2 matrix. Then A has an inverse, which can be found using this formula. A inverse is the reciprocal of the determinant of matrix A multiplied by the so-called adjugate of matrix A, where matrix A is labeled ABCD, meaning it is a 2 by 2 matrix, and its adjugate version is temporarily called B, which is formed by swapping the diagonal elements in matrix A and changing the signs of the off-diagonal elements. How do I prove that what I just said is true? Yes, I prove it by first just noticing that if I multiply matrix A by that special matrix B here, then when I do that, I get this. And I recognize that as representing the determinant of matrix A, because AD minus BC is exactly that, times that minus that times that. And that's the definition of the determinant for a 2 by 2 matrix. And at the same time, I recognize this matrix as a very special simple one called the identity matrix of order 2, because it is 2 by 2. So what I know now is that a times B gives what? It's simply that from a times the identity matrix, well, then I can just divide by this number on both sides, which is the same as multiplying by its reciprocal, and I multiply it on the B side, as it turns out to be clever to prove that it's valid. And what I now realize is that the A matrix multiplied by this matrix. How do I know this is a matrix? Well, B was a matrix, and a number times a matrix gives a new matrix. So I have found a matrix here that when I multiply A with it, gives the identity matrix. Well, then what I have found here must be exactly what I mean when I talk about the inverse. For the inverse is something I can multiply with to get a simple one. It's a sneaky one. It's a one written in matrix form. And there's the proof, because B was precisely the temporary name for the adjugate version of A. So let's pause the recording, Sophie, and then we'll just go out and practice it. And what should we say? It will probably take until about 10 to get out and practice it.